We continue now in Chapter 1 with Lecture 3, which is the design of the CSTR, deriving the CSTR design equation, and then give an example of how one uses a CSTR. CSTRs are used primarily for liquid phase reactions. The advantages are they have good temperature control, virtually no hotspots, and little, if any, product variation. The disadvantages are mixing can be a problem. We can have some dead volumes where the circulation doesn't get down to, say, the corners of the reactor, and this takes up space that the reaction could be taking place in. We can have some bypassing that takes place where the reactants don't get well mixed with inside here. The other thing is for CSTRs, they usually require large reactor volumes because the rate is usually slow and is operated at its lowest value in the reactor. So CSTRs are used by themselves. Now, CSTRs are well mixed in the sense that the concentration at the exit is assumed to be the same as the concentration inside the reactor. And also, the rate of disappearance of A at the exit concentration is the same throughout the CSTR. CSTRs are not only used by themselves, but they can be used in series as a number of CSTRs. We start with our basic building block, which we did in Lecture 1. That is, what comes into the CSTR FA0 minus what goes out, plus the rate of generation of species A in the CSTR is equal to the accumulation. Now, for a CSTR operated at steady state, this term we'll see is going to be equal to 0. So here's our balance on our CSTR, again, with the accumulation term equal to 0. That is steady state. We also considered the CSTR to be well mixed. We said that the rate was everywhere the same within the reactor. So this is invariant with reactor volume and can be taken outside the integral sign, in which we just have the rate of generation is just RA times the reactor volume. So this brings us to our mole balance in this form. In minus out plus the rate per unit volume times volume is 0. Rearranging, we have our basic design equation. This gives us the volume V necessary to reduce the entering molar flow rate from FA to an exit molar flow rate, FA, where the rate of reaction in the reactor is occurring at minus RA. So let's do an example now. Let's calculate the CSTR volume necessary to reduce the exit concentration to 10% of the entering concentration. We're going to be given the specific reaction rate is 0.2 reciprocal minutes, and the volumetric flow rate is 10 decimeters cubed per minute. And the question is then, what is the volume necessary to carry out this reduction in concentration from CA0 to 0.1 CA0? Well, the general design equation for a CSTR, as we just derived, was that. RA is the reaction. We're again going to assume it's first order, as we did in the batch reactor example. And we're also going to now substitute for the molar flow rate FA0, and FA0 is the concentration, moles per unit volume, times the volumetric flow rate, decimeters cubed per minute. So the units of this will be then moles per minute. And likewise for the exit concentrations, the concentration of A, moles per unit volume times the volume, decimeters cubed per minute, and again it will be moles per minute. Now for liquid systems, the volumetric flow rate is almost always constant. So if we substitute now for FA and 0, and for FA, and for the rate law, we arrive at this equation. We want to find V for CA equals 1/10 the entering concentration. So this is the equation we had in the previous slide. We have now CA0 V0 minus CA times V0 because the volumetric flow rate is going to be constant. And also we have now that Ca is 1/10 Ca0. We're going to factor, and likewise here, the concentration of A is 1/10 Ca0. So we're going to substitute for Ca here and also here. And then we see when we do this, we're going to be able to cancel Ca0 in the numerator with Ca0 in the denominator, which just leaves us V0, the volumetric flow rate, times 1 minus 0.1 over 0.1 K. Substituting these values in, we find the volume necessary to reduce the concentration in a continuous stirred tank reactor from a Ca0 to 0.1 Ca0 will require 391.3 decimeters cubed. So this essentially then is the end of Chapter 1, Lecture 3, and the equation we derived was this, giving the volume V, and then we get an example showing how to apply this to a specific situation.